interpreted.
So for the first one, a power of our algebraic numbers, remember we take the power of the count. 2 to the 8th power is 8 2's multiplied together, which is 256. And then for the powers, x to the 4th to the 8th power, we multiply the powers. 4 times 8 is 32, so that's x to the 32. Y to the 3rd to the 8th power, well, 3 times 8 is 24, so that's y to the 24th. So we get 256, x to the 32, y to the 24. For a root, remember, we take the root of the number, and then we divide the powers. This is a square root, so this is really a 2 here, so we're going to be dividing the powers by 2. Well, the square root of 144 is just 12. We still take the square root of the count, or the number. Square root of x to the 8th, well, 8 divided by 2 is 4, so that's x to the 4th. And the square root of y to the 12th. 12 divided by 2 is 6, so that's y to the 6th. So today we're going to be shifting gears a little bit. There is a quiz out there for you, by the way, quiz 1115. Which is due at noon tomorrow. Is that October 29th? So make sure you don't miss that. As I said, today we're switching gears just a little bit, and we're going to be looking back at numbers and away from the variables for a while. We're going to start out by looking at our powers of 10. Of course, we know that 10 to the 3rd power is 10 times 10 times 10, or 1,000. In fact, many of you have worked with powers of 10 enough to know that a 10 to a power of is just 1, followed by the number of zeros that the power is. 10 to the power of 7 would be a 1, followed by 7 zeros, or 10 million. Well, with that in mind, then, we can work with our powers of 10 just like we would with our variables. If I had 10 to the 5th times 10 to the 9th, I'm multiplying exponents with like bases. They both have a base of 10. I can add the powers. 5 plus 9 is 14. That's 10 to the 14th. Also, we can use the powers of 10 to help us define what a power of 0 is. If I put up 10 to the power of 0 and ask people what it is, a lot of people would say 0. And that does kind of make sense, but that's not what it comes out to be. Just like with our integers, our negatives, we look for a pattern. 10 to the power of 3 is 1,000. 10 to the power of 2 is 100. And 10 to the power of 1 is just 10. And what we notice here is every time we reduce that power by 1, our answer here is divided by 10. 1,000 divided by 10 is 100. 100 divided by 10 is 10. So if we keep going and do 10 to the power of 0, we have to divide this by 10 again. We've reduced the power by 1. We divide the result by 10. 10 divided by 10 is 1. So 10 to the power of 0 is 1. In fact, anything to the power of 0 is 1. Y to the power of 0 is 1. Or x to the power of 0 is 1. Anything to the power of 0 is going to be just 1. Now we can use this pattern to define what negative powers mean. If I go 10 to the negative 1, I've just reduced the power by 1 again. I'm going to divide my result by 10. 1 divided by 10 is 1/10. 10 to the negative 2, I divide by 10 again. 1/10 divided by 10 is 1/100. 10 to the negative 3 is going to be 1/100 divided by 10 is 1,000. And we see a pattern developing here between our positive and our negative powers. 10 to the negative 3 is just the reciprocal of 10 to the power of positive 3. 10 to the negative 3 is just 1 over 10 to the third. And that'll always be true. A negative power is just a reciprocal. X to the power of negative 2 really is just x, or 1 over x to the power of 2, x squared. Excuse me. So we can combine powers here. We might have 10 to the 8th times 10 to the negative 13th. We are multiplying here. We have like bases. Both of those exponents have bases of 10. So we're going to add the powers. 8 plus negative 13 is negative 5. That is 10 to the negative 5.
Recording is on.
We're going to have 10 to the negative 5th times 10 to the 18th. Again, those are exponents with the same bases. They both have bases of 10. This will be 10 to the power of negative 5 plus 18 is 13. Division is where it becomes a little trickier with these negative powers. If I had 10 to the 11th divided by 10 to the 6th, I am dividing exponents with the same base. So I subtract the powers. 11 minus 6 is 5. But if I have 10 to the negative 7 divided by 10 to the 8th, again, I still have the same base in my exponents. They're both bases of 10. But it's the power will be negative 7 minus 8. Negative 7 minus 8 is negative 7 plus a negative 8, which is negative 15. So that's 10 to the negative 15th. Or we might have 10 to the 6th divided by 10 to the negative 12th. Well, again, they have the same base, so we're going to just combine the powers. 6 minus a negative 12 is just 6 plus 12, or a positive 18. So that's 10 to the positive 18th. Excuse me. So I might have 10 to the 8th times 10 to the negative 5th over 10 to the negative 7th times 10 to the 4th. That fraction bar is telling us that we have to do everything on top first, then everything on bottom, and then divide. So on top, we're going to multiply 10 to the 8th times 10 to the negative 5th. Those both are exponents with bases of 10, so we're just going to combine powers. 8 plus negative 5 is 3. On bottom, 10 to the negative 7th times 10 to the 4th is 10 to the negative 3. And now we are dividing here. That'll be 10 to the power of 3 minus negative 3, which is 3 plus 3, or 10 to the 6th. So why am I spending all this time working with powers of 10? Well, let's go back to our place values for our numbers. This is the ones place, the tens place, the hundreds place, the 1,000s, 10,000s, 100,000s. Now I wrote those out numerically for a reason, so that we could see the pattern with our powers of 10. That's the 10 to the 0, or the ones place. 10 to the 1, which is the tens place. 10 to the power of 2 is the hundreds place. 10 to the third is the thousands. 10 to the fourth is 10,000. 10 to the fifth is 100,000. 10 to the sixth is 1,000,000, and 10 to the seventh is 10 million. Even going after the decimal point, 10 to the negative 1 is 1/10, and 10 to the negative 2 is 100th. 10 to the negative 3 is 1,000th. 10 to the negative 4 is a 10,000th. And 10 to the negative 5 is 100,000th. Our place values are simply powers of 10. Our number system is a decimal number system. Deci means 10, or sometimes referred to as a base 10 number system. That means our place values are exponents with bases of 10. If you look at other numbering systems, if you get into like computer programming and stuff, you would look at binary number systems. Binary number systems are a number system where the place values are exponents with a base of 2 rather than a base of 10. That's how computers think and how machines think. So let's take a number like 3,700,000. Often we would shorten that by writing it as 3.7 million. Well, we don't have to write out the word million, as we've seen. We can just do 3.7 times 10 to the 6th, because 10 to the 6th is the million. Some of you might be recognizing this as scientific notation. In scientific notation, what we do is we identify the first non-zero digit. So in this case, that would be the 3. We put the decimal point after that digit, so that's why it went there, 3.7. And then we name the place value of that digit. It's in the 10 to the 6th place. So if I had 0.00072, my first non-zero digit is the 7, so I'm going to put my decimal point after that. That's going to be 7.2. And the place value of the 7 is 10 to the negative 4, so times 10 to the negative 4. Now, when I convert numbers into scientific notation, I don't want to have to draw out the place values every time so I can do it. So there is a shortcut for converting. Most of the time, if we're using scientific notation, we have either really large numbers or really small numbers. So it's, powers of 10 to the negative 20th or positive 20th or whatever. We don't want to have to write out the whole place values that far anyway. So if I look at my 3.7 times 10 to the 6th here, the decimal point there wasn't one written, so that means it started at the end of the number, and we moved it over to here. So it moved 1, 2, 3, 4, 5, 6 spots, hence the 10 to the 6th. That was a large number. By large, I mean it was bigger than 1. So it was in the positive power of 10 place values. That's why it's a 10 to the positive 6th. Over here, the decimal point started out right here, and we moved it over to here. It moved 1, 2, 3, 4 places, hence the 10 to the 4th. That was a small number. Again, by small, I mean smaller than 1, which means it was in the place values that were negative powers of 10. So that's why it's 10 to the negative 4. So if I want to convert, like 0.0000089, I identify my first non-zero digit. That's the 8 right there. So I'll move my decimal point so it's after the 8. Then I can move my decimal point. It moves 1, 2, 3, 4, 5, 6 spots. That's 8.9 times 10 to the, is that going to be positive 6 or negative 6? Well, that's a really small number. It's smaller than 1, so it's going to be a negative 6. It's in the place values that are negative powers of 10. If I take 420 million, again, the first non-zero digit is right there, the 4. So I'll move my decimal point so that it's after the 4. Right now it's not written, so that means it's at the end of the number. So it had to move 1, 2, 3, 4, 5, 6, 7, 8 places. That's 4.2 times 10 to the 8th. That was a large number, so that is a positive 8 on the power of 10. So converting our numbers into scientific notation is pretty straightforward, pretty simple to do. Going the other direction is pretty simple as well. I have 4.9 times 10 to the 5th. I start out with my 4.9. With 5, 10 to the 5th means I'm going to have to move my decimal point 5 spots. I have to decide if I'm making this number larger or smaller. Well, that's a positive 5, which means I'm making this number larger. So I have to move my decimal point 5 spots to make this number larger. So I go 1, then I have to add zeros, 2, 3, 4, 5. So that is 490,000. We might have 3.8 times 10 to the negative 7. Again, I start out with my 3.8. That power of negative 7, first of all, it's negative, which tells me this is a small number, so I'm making it smaller. 7 tells me I'm moving it 7 places to make it smaller. So I move 1, and then I have to add zeros. 2, 3, 4, 5, 6, 7. So that is 0.000038. So like I said, the conversions are relatively simple. Well, on top of scientific notation, we have something called engineering notation. For scientific notation, we had to have 1 digit before the decimal, and it couldn't be a 0. And the power of 10 could be anything. Whatever it took, however many places we had to move the decimal point. For engineering notation, our power of 10 is restricted. Power of 10 must be a multiple of 3. So that means 3, 6, 9, 12, 15, or negative 3, negative 6, negative 9, and so on like that. And there can be 1, 2, or 3 digits before the decimal. So what does this mean? Well, let's take a peek. Let's take 28 million. Basically, this here, that our power of 10 has to be a multiple of 3, means we have to move the decimal point 3 spots at a time. So we start here, there's no decimal written, so it's at the end of the number. So we go 1, 2, 3. Well, we can go 3 more, so we'll go 4, 5, 6. We cannot go 3 more. So that's 28 times 10 to the 6th. Where the engineering notation can be really tricky is in numbers like this. 0.00057. We move our decimal point 3 spots at a time. We go 1, 2, 3. We ask ourselves if we can go 3 more, and at first it looks like we can't. But if you look closer, we have to. Right now, all that's in front of the decimal point is zeros. We have to have 1, 2, or 3 digits before the decimal point that are not zeros. So we have to go 3 more. We go 4, 5, 6, and we add a 0 there. So that's 570 times 10 to the negative 6th. Well, why do we have this engineering notation to confuse things? Well, because the engineering notation is our metric measurements. In other words, our metric prefixes. We have our main unit, whether it's a meter, a liter, whatever. Could be an amp, could be a volt. If we're dealing with electricity. We have those main units. And we said we tend to not use the 1/10 and the 1/100th. We tend to skip to the milli, which is 1/1000th. Well, that's 10 to the negative 3. Then after that, we don't even have prefixes for 10,000, 100,000. We go to micro, which is a millionth, which is 10 to the negative 6th. Then we go to nano, which is a billionth, or 10 to the negative 9th. Going larger, we tend not to use the 10 or the 100. We go to kilo, which is 1,000, or 10 to the 3rd. Then we go to mega, which is a million, or 10 to the 6th. Then giga, which is a trillion, or 10 to the 9th. And then tera, which is 10 to the 12th, and continuing on. We actually have prefixes up to 15 in both directions. Well, why do we care? Well, let's say if you're looking at an electrical concept, you might have something that's running 40 milliamps. Well, what does that really mean? Milli is 10 to the negative 3. So that's really 40 times 10 to the negative 3 amps. Or you might have 2.4 mega ohms. Well, mega is 10 to the 6th. That's 2.4 times 10 to the 6th ohms. When we look at doing operations with scientific notation and engineering notation, it's this engineering notation that allows us to do operations with our metric prefixes. We convert the metric prefix to the appropriate power of 10 in engineering notation, and then we can calculate and convert back. Okay, well, for today, I think I have talked as much as I can talk, so we are going to give you some homework. Don't forget, there's that quiz out there to do. 11:15 that is due tomorrow. We're kind of in a stretch here where there's going to be a quiz every hour or two for a while. I apologize for that, but a lot of material that we're going through here in a short period of time. For homework, we're in the big book. Pages 246. Exercise 6-11A. Page 246, 247. Exercise 6-11B. Page 252, 253. Exercise 6-12A. And page 254. Exercise 6-12B. Of course, on all those, you just need to do the odds. Practice with these tomorrow. We will look at operations with our scientific and engineering notation. And then we'll be wrapping that part of it up.